In this video lesson, we're going to talk about how density now relates back to this idea of mass and volume. And we're going to spend most of our time talking about how we can model density in different ways, shapes, and forms. Okay, so let's start off with kind of our definition. So actually defining density and using sentence structure is actually one way you can model density, right? So density is a comparison of how massive a substance is in comparison to the volume it takes up. So if you think about that, another word we might want to use here, it's a ratio. So it's a ratio of mass to volume of a substance, which means the more massive you are, the more dense you could be, or the less volume you occupy, the more dense you could be, okay? So it's a comparison between those two things, all right? So when we first talk about density, we probably want to take a look at some different objects. Now, I have two objects here. Now, the problem is you can't feel these because you're watching a video. So you have to go by and trust what I'm saying here. So these two objects, if we look at them, they have the exact same dimensions to them, which means their volumes are equal. In my hands, though, this object feels much heavier to me. This object feels lighter to me, okay? So as a result, because they have the same volume, and this one feels heavier, it feels more massive, okay? That means more mass, same volume, this one should be more dense than this one, okay? So that's kind of a visual thing for us to look at. Another two examples, here we go. We have same two materials, okay? And now when I put them in my hand, they feel like they have the same mass. So I set them nice and flat, that mass versus that one, yeah, okay? They feel like they have the same amount of mass, which they do. But this one, I mean, if you look at it, it's like 1, 2, almost 3 times taller. And because their diameters are the same, it's actually going to be 3 times the volume, okay? So here, same mass, but way more volume in for number 1 right here. So high volume, same mass. This object here is going to be less dense than this object here, okay? Or other way of saying this would be more dense of our objects, okay? So we're going to keep that in mind, that it's a comparison between the two. Now, mathematically, we could also represent this, all right? And so when we start talking about modeling of things, we can represent things and model things mathematically, first of all. So let's talk about how we can do that. So if we knew the density of something, okay, because it's a ratio of our mass to our volume, that lends itself to writing a formula. And a formula is really a mathematical model for our density, okay? And then a lot of times in the sciences, we like to shorten these formulas down to just use symbolism. So we're going to use D for density, a capital M for mass, and a capital V for volume, okay? And then also a lot of times when we represent formulas or mathematical models, we include the units that we're going to be using. So mass, we typically are going to be measuring in grams, and volume in here is usually milliliters. Now that doesn't mean that, kilograms per liter isn't valid. This is still represents density, but it's just not a unit that we're going to use very often, okay? And we never use things like pounds and fluid ounces and gallons and that kind of stuff, because really there's only like one country in the world that still uses that thing, and even their scientists don't use them, so we kind of ignore that stuff, okay? So we have our mass divided by our volume, okay? Now, mathematically speaking, we're not going to practice this formula, okay? It's a 3-variable formula that you should have learned how to manipulate and solve for probably starting in 6th grade, okay? So are you responsible for being able to solve for density or find the mass of something if you know its density? Absolutely. And we'll actually do that mathematical work in one of our labs, but we're not going to do it in part of our lecture because, again, I think it's math you already can do. All right. Now, as we continue on this idea of density modeling, we want to talk a little bit more about what is modeling, okay? Now, there's all sorts of types of models, right? There's model cars, there's model airplanes, there's fashion models, all kinds of things that we use for modeling, all right? Businesses model certain practices, those kind of things. And they all actually have a lot of similarities to them, okay? Whenever you model something, whether it be a scientific model, whether it be a non-science model, you're trying to represent something that's more complex or hard to visualize or rare or something that's just, you can't just look at it and know what it is in its own form, okay? So for example, if you want to model the cell of an atom, okay, we can't pop a cell out of our body and go, oh yeah, that's a cell, cool. We can't look at that. So we have a model of that where we draw things and we visualize it to help us understand the cell of an atom, or the cell of one of the cells in our body. It's not a cell of an atom, sorry, the cell in our body, okay. And then we model that model. So, like, well, how does a cell in like an animal differ from a cell in a plant? Okay, so we use the same system so those two cells can be compared. Okay, so a good model will also be able to link back to other models and then use similar ideas, similar comparisons, those kind of things. Okay, we need models in the sciences because we can't see everything, and there's a lot of complexity to what we understand how our universe works. Okay, so by modeling things, we're helping visualize, simplify, and understand the complexity of our universe. Okay, and modeling is one of those tools that we use across all the sciences, whether it be modeling plate tectonics in earth science, or modeling the universe in physics, or modeling, the endocrine system in biology, or modeling the actual structure of an atom in chemistry. We all use models for those kind of things. All right. Now, aspects of a quality model, okay? Things you need to have. One, it has to be reproducible, which means you can apply that model across all examples of whatever you're trying to model, okay? That's why fashion models, I don't know if I should use the term model for that, because when I look at fashion models and the clothes that they have on, I rarely see a person who has my body shape and size, and I don't think how that looks is going to look the same on me, okay? Now, I think I look good, but I don't think it's going to line up very well. So, but it should, okay, transcend multiple examples of it. It should actually visually represent what you're actually trying to model, okay, those kind of things. And it should be applicable under multiple scenarios. So if we're talking about modeling density, I should be able to apply that to, let's say we're modeling density of metals, like my two objects from before, okay? I should be able to build a model where, whether it's really dense or less dense, whether it's low volume or high volume, the model can represent all those different permutations of density. Okay, so as we look at modeling, that's what we want to look for, is its flexibility, but also being as simple as possible. Okay, and then finally, all models need to have a key. Okay, so for example, when we did this mathematical model originally, we use words to represent stuff, and we know mathematical formulas and bars. We have a certain amount of knowledge on them, so we know what the equal sign means. We know that something written with a bar between it is a division bar. So we have a key. It's a mathematical key to formulas. Okay. Sometimes when we do visual models or graphical models, we need to provide more of a key for that stuff. All right. So let's do that now. Let's take a look at these densities. We're actually going to use these two substances as our choice here. And we're going to represent a model that allows us to deal with all four scenarios in one model, okay? So to start that, I'm going to draw two circles. I'm going to draw a circle here, and I'm going to draw a circle here. Okay. Now, in my model, the circle has no bearing. Okay, so I'm starting to build my key. All right, so the size of the circle, so this circle being, this big versus this circle being that big, has no bearing on my model. So I've identified that for you as we do this. Maybe in a model that you choose, the circle size would have a place in your model. Okay, but in my model, it does not. All right. So that is my first thing. Now, I want to find a way to visually represent mass. Okay. So in this case, how do I want to do mass? I have some options. I could use a bunch of little dots. I could use big dots, small dots. I could use a color system. I could use blue versus red. Okay. Think of like a radar model when you have a model of like storms coming in. Most people know that the standard model for radars is green means rain, yellow means hard rain, maybe some wind. Red means really windy, potential thunderstorm, lightning, kind of dangerous storms. And if you get to purple, it means duck and cover because something big is coming at you. Okay. So that's how we know that that model has a key to it. For my case, I have a choice. I can use lots of dots to represent mass, or the number of dots, or the size. So I'm going to use size. So I'm going to say the mass equals the size of my dots, okay? So in that case, if I have high mass, I'm going to draw really big dots inside my model. Okay, so if this would be high mass, this would be low mass, I would draw smaller dots inside this model. Okay. Now notice in my low mass model, I put more dots in, but the number of dots has no bearing on the mass. So visually, you should look at this and say, oh yeah, I see bigger dots. So here, if I circle these, I see bigger dots. So there's more mass here, okay? I see smaller dots, there's less mass here. The number of dots doesn't mean anything, okay? Maybe your model, the number of dots would mean something. So maybe you're going to use all the same size dots, and instead of it being the size, we could say that mass represents by the number of dots. So high mass will be represented by the number of dots, okay? One's not better than the other. It's just however you represent your model, okay? In terms of what you're doing. Now, I'm going to go backwards here a little bit. You can choose whatever you want to. So we're going to go back to where size is our thing. So here we go. That's part of my picture. The other thing I need to represent is my volume. Okay? So because I said the circles themselves have no bearing, the perimeter of that isn't my volume. So instead, my volume is going to be the space between the particles. So whatever space I have from here to here, that in-between space, I might want to show it a little bit. Maybe I'll show it like this, from like here to here, or here to here. That represents the relative volume of my substance. That way, if I have a really big thing, really small thing, I can just use spacing versus having to draw a bigger circle versus a smaller circle. Okay? Again, it's my choice of my model. Now, a person looking at this idea, if they see my key here, and they look at this, they can say, oh, these have big dots, so it's high mass. The space between them is about the same, so the volume isn't really different. So this would be high mass, same volume. Okay, so of my four objects, looking at these things then, okay, I have same volume, high mass. So this would represent my more dense thing here. Same volume, low mass would represent the low mass one, okay? And then we could modify this to represent high volume, low volume, and vice versa, okay? So it becomes a good visual model to represent density by comparing, again, mass to our volume comparisons here, okay? So that's one way to do it. That's a visual model, okay? We use lots of visual models in science, for density especially. Now, the last model type that we want to talk about is graphical models. So how do we graph density, okay? Probably a very useful tool for us because density is a relationship, right? It's a relationship between mass and volume. So anytime you want to graph something where there's a ratio or a relationship or a cause and effect kind of thing, where if you change one, it changes something else. You usually want to use a line graph or a scatter plot of some sort. Okay, so as I graph this, and we take a look at that, one possibility is I want to put my mass in grams, maybe on my x-axis, sorry, my y-axis, and maybe I want to put my volume in milliliters on my x-axis. Okay, now as I graph different things, so let's say I take these two objects. They have different masses, they have different volumes, but they both have the same density because they're the same material. These are both copper. So I can put both of these on my graph, okay? I have one with high mass and high volume. I have one with lower mass and lower volume. So I should be able to do a line of best fit from those 2 points, okay? Again, not perfect 'cause I'm measuring, okay? Again, I have volume versus mass, two different objects, and I should be able to do that also for the aluminum. So maybe I have, that one's a little more volume, so it'll be here, and that one's the same volume, so I should line that up with that dot there. And then now, doing my line of best fit, we can represent that also, okay? Now notice, we know that density is mass divided by volume. So graphically, it's our rise over our run. Okay? So graphically, what we're saying here is that the slope equals density. Now the power of this is, no matter what object I have, if it's made of copper, it should fall on that line. If it's made of aluminum, it should fall somewhere along this line, okay? So with a simple sloping line or a simple linear regression, we can now track the density or the mass and volume of any object that's made of aluminum, or the mass and volume of any object that's made of copper, okay? And it's a very simple graph as we look at it. So graphically, we can also represent density as we take a look at these things, okay? So there you go. We looked at a mathematical way to represent density, a model using math formulas. In the notes, we had a verbal way. We have a visual way to represent a model of density, and we have a graphical way to represent a model of density. Okay? In all cases, they're quality models because we have a key for them. They can be applied across any scenario that has these metals inside of them, those different densities. They're simple to read, and they actually represent what we're looking for them to do. Okay, so that's good modeling technique. All right, that is density, and that is modeling with density. Thank you.